Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on a water sloshing problem. So right now on my screen what you see is a rigid tank. Inside that there is a water, and then the tank go through deceleration and then water gets sloshing. So as tank go through deceleration, water just hit the front surface and it starts sloshing within the box, and the box here actually we assume a rigid to do a quick problem. So this is what you see is the water behavior, water sloshing inside. You can see some droplet forming, so just water leave and then droplet forms. And if you do quite a bit fine mesh, you can capture a lot of things. So we are not done that quite fine mesh, but we're done mainly to capture sloshing inside the tank. And then this type of problems are a lot of people do this to find water behavior, stresses on tank. So we are going to do this. So do a water sloshing inside a tank. It's a typical transportation vehicle. You filled with water and then you apply sudden braking. So this case we have put a 20 km/h, then there is a sudden braking, very short duration there is a braking, and water start getting sloshing. That is the exact problem we are going to do. We have taken a thin structure, but then just a demonstration purpose we are done. But for your problem you can actually model what is your problem. So before going into problem, let's go through what exactly we are going to go. So let's go to the problem definition. Once we clear about the problem definition, then we can talk. So we are going to do water sloshing using CEL technique. Capability within Abaqus explicit. The only CEL is only available with Abaqus explicit. And this is our second video on the couple Eulerian Lagrangian. Our first video was on can drop test using CEL. We'll recommend you to watch that also, so you'll get familiar with the CEL technique. The problem what we are going to do is we'll have a rigid tank, and the tank is not fully filled, it is a partially filled tank. So you see a fainted yellow color is partially filled water, and that's what actually using volume fraction of assembly we have seen. This is the red color is a partially filled, and then this blue color is your domain. So it's a Eulerian domain rigid surface, and you give a deceleration to tank. Since this tank will be on the vehicle will going with some speed, say in this case it was a 20 km/h. So water and rigid surface everybody take that velocity. So all this will be at 20 km/h velocity, and then you put a brake. So vehicle put on a brake, that causes this rigid box to come to rest with a quick deceleration from 20 km/h to 0, and then you keep the brake, and then you see how the water gets sloshing inside this. So this is the problem. Now we are just going to use typical water problem. Density, equation of state, viscosity. The unit which we are going to use a ton, millimeter, Newton second. Partially filled tank, so rigid box is 100 mm by 10. The depth we have taken a 10 mm, just because we want to just quickly solve the problem. We don't want to run it more time. Your box can be deformable. It can be a metal box or metal tank or different shaped tank. So it depends on you. It can be deformable. Our case we want to do quickly, so we taken a rigid box. Then water is partially filled. So total height is 60, but the water is filled by only with a 40 mm, and we have a Eulerian mesh of 300 by 70 mm. So once tank go through deceleration, you can have this Eulerian mesh throughout the mesh, and then only the material is going to pass through cell by cell. Not mesh is not going to deform anything. So that is the beauty about this CEL technique. Problem what we are going to do, as we mentioned, we are going to run for 20 milliseconds. So we are going to give a box 550 mm/s velocity, which is equivalent to 20 km/h, and then sudden duration, short duration from 0, the time 0, we are going to bring this amplitude to 10 millisecond to 0, and then we are going to keep it constant. So at 0 time we have full amplitude 550, and then at 0.01 we are going to bring it to 0, and then for 0.2 we are going to keep it 0. So this is the triangular profile. We are going to give deceleration, and then we are going to keep it 0. So there will be sudden deceleration, and then deceleration we will going to keep it 0. Since this tank is mounted on a vehicle, so the water will also get velocity what vehicle is going. So vehicle is going with a 20 kilometers per hour. So the Eulerian mesh also we have to put a 550 velocity along with a box deceleration. And same time when this is going on, there is a gravity load applied. So gravity is applied from the top. So that what actually you see 9810 minus 1 in y direction. So the gravity is also working, and then we are going to see the effect of sloshing. So this is a problem we are going to do. Let's start doing the problem. So just at the end we are expecting that it should get a sloshing. So let's say new, no. So what we'll do first we'll build Eulerian mesh. So create, you give name, I'll put Eulerian EUL 3D Eulerian mesh extruded surface, and we are going to model this by 300 in length, and then 70 millimeter in depth, and 10 millimeter in thickness direction. So let me put this as a 400, and then let me quickly put 0, 0, and then I get a center reference, and then we want one point here, minus 150 minus 35, and we want one more point 150 comma 35, so that is come to 300 by 35. So this is Eulerian domain. Let's check the dimension. Is 70, perfect, and then let me check this 300, perfect. Now we'll extrude this by blind 10 millimeter. So we got a Eulerian mesh. Now we just want to have a low depth, low thickness, because just to solve this problem. But your actual case, it may be when you solve your problem, your tank will be deformable, depth can be on higher side. Now once we done that, we'll quickly create the water property. So density is 940 kg per millimeter cube. We are going to use is a ton per kg per meter cube. We are going to use ton per millimeter. So 0.95 e power minus 9, and then we'll give equation of state USUP, and this is like speed of sound inside the water, and that's what actually we put 1.54 e power 06, and then we'll have viscosity. So we define the water, we'll define Eulerian section, and then you say water, instant water, and then we assign that. So we define a Eulerian domain with water property. Now we have to create one rigid box, and then box filled with partial volume. So we want one more dummy surface to partially fill it. So first let's create, it will be 3D discrete rigid, it will be solid, then we'll convert it solid to this. So 200 will be will give 300 will be good enough, and this will be box. So 3D discrete rigid solid extrusion approximate sides 300. We are going to put 0, 0, then minus 50, 30, sorry, minus 50, minus 30, and then 50, 30. So that way we can get two corners. Let's quickly check the 60, perfect, and then check this is perfect, and then we are going to give a depth 10 millimeter as a blind. Now guys, this is solid. We need to convert into shell, so this is important step. If you miss this, then there will be issue to execute this problem. So what we are done, we are 3D discrete rigid and we created with the solid. Now what we'll do, in part itself you have option shape, shell from solid, and then you select that. So this will be converted into a shell, so we can properly put the boundary condition. Now in the property we'll give a reference point. I'll just assign this as a reference point. So I have reference point mark here. I'll also create quickly a set for reference point, because we are going to give a deceleration on this point, and this point will be, we also put a boundary condition. So box everything done. Now we'll create one more part, because we want this liquid should be partially filled, not fully filled. So for that, so we can see a sloshing inside. So how we are going to fill it? So we are going to fill it using in a typical tool for volume fraction, but for that we need a closed volume. So we are going to create one dummy deformable. We are going to put one dummy, and then dummy will suppress it later. And this liquid is partially filled, so I'm going to put minus 50, minus 20, and then 50, 20. So that way I can create something partially filled. I can see this point here, and this point is here. Okay, perfect. Let's check. This is 40, perfect. Is this 100? Perfect. No, and then extrude by 10. So I got one dummy. I just created dummy. This will also I'll convert from shell from solid, and I'll just convert into shell. Now we created 3-part: box, dummy, Eulerian mesh. Eulerian we are given a water property, dummy we don't have to give anything. We are going to suppress this part, and box we have created a rigid definition we have created. Now we'll quickly create instant, and let's do one thing. First let's put this water, you see it's middle filled, so let's put it down, because so first we are going to say dummy, we are going to take dummy, and this point we are going to bring to this point. So dummy mesh is come, and then we are going to use this for partial filling. And the other things what we'll do is position Eulerian part from this to this, so they are aligned. The only thing we'll take this down and then little bit back. So I'm going to translate this 0, minus 5, 0, so they come in center, and then I'm going to take it Eulerian mesh back -5, 0, 0. So 5, 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 So you have domain mesh, then you have rigid box, and you have this dummy. We are going to fill it. Now we'll quickly mesh this. So once we mesh it, then we'll see how we can fill it. So I go to mesh. Dummy is just for a filling purpose, so you don't have to much worry about it, and we're going to suppress it. But let's have a quick good structural mesh. Box will create box. We are going to just put a bit fine mesh just for the contact purpose. So let's contact work very well. If you have good fine mesh, then you also get quite a bit good. So we are going to put 2.5 just to get a good contact with rigid box, and then we have Eulerian mesh. This is already, it's the EVC element EC3D8R. So it's a 8-noded linear Eulerian brick. Explicit, it's available. Structural mesh, what we are seeing, we are also saying this 2.5, and then we got a fine mesh. Now we got all three mesh, we box, dummy, and Eulerian. Now let me save this file. So water sloshing. So let's go to interaction, and here we are going to use tool discrete field. So this is important field. You'll get this only in interaction. So after you go to interaction, go to tool, go to discrete field, and you say volume fraction. So once you see volume fraction, you see the bottom message what it's saying. Select the Eulerian part instant. So we selected Eulerian, and it says select the reference instant. So reference instant is the inside what you want to fill the water. So we want to fill it inside the dummy. Then it will ask accuracy what you want, low, medium, high. I say high. I also say I want node set for both these, and then inside reference instant. So it's a computed volume fraction, it start filling. So you see it start filling. Now it start filled. Now important things, very important thing, you have to give reference material for this. It filled, but what material? So we want to assign the material. So you go to load, you go to predefined fold, and here you create inside water identity, other material assignment. You go again, select the Eulerian mesh, discrete field, whole part, and then here you select water, discrete field water. So you now complete the definition of volume fraction. You selected volume, inside that you filled water, you give an identity. So this is now we are done this. Now since we have meshed this Eulerian, I want to create a node set. So I am going to select all, because we want to give an initial velocity on that. Now I'll go to the load, then predefine, create mechanical water velocity. It will be initial velocity. Then you select water node, and then this will be initial velocity. You are going to give in positive x. So positive x 5.5 e power 03. Dismiss. So you see all Eulerian domain we are given a velocity. So how it is going to take? This velocity is only going to applied wherever there is no void. Wherever there is a water, it is going to apply. So even though this will be all void, so it is not going to apply the velocity seed. So only going to apply velocity where there is no void. So there is zero void. So this refer to 1, and wherever this inside water, that's where actually it's going to apply the velocity. Now we done that. Now we'll quickly create a step. Water sloshing. It will be dynamic explicit and 0.02, and now we'll apply couple of loads. We'll first apply gravity, so gravity will be minus 9810 in y direction. We apply gravity. Now we are going to put deceleration to the box reference node. So this will be inside step, deceleration water mechanical. You select a velocity, and then you select a box reference point, and then we say it will be in y. We are going to apply 5.5 e power 03. Not instantaneously, we are going to have amplitude. So time is equal to 0. This velocity is applied because everything is going with initial velocity. You start driving the truck. In this truck you have this water container inside, and inside that there is water. So everybody got a 5500 millimeter per second velocity. Now for 0 time everything is there. Then you put a brake, and this is the very high deceleration. So even immediately 0.01 second you put a brake, and it's everything come to 0, and then 0.02 it is at 0. So this is what triangular pulse, and then you are giving some time to it, and then we say it's amplitude. Now we'll go back. We created three parts. We created dummy part for filling purpose. We assign property. We created section property. We fill the water, everything, and we created a step. We given a g load. We given a all velocity. We are given a deceleration. Now we'll also define a contact. So we are going to create a friction property first. So normal behavior will just keep default, and tangential behavior will put some friction 0.2. Since it is a water, it will have very low friction, but just we are going to put 0.2, and then we are going to say automatic general explicit, and that. Now guys, most of our things we are done. Only one thing is pending. Now this is important, otherwise you will get a error. Let me save it. So we are going to make dummy in instant. We are going to say suppress it. We don't want to express it. So we suppress it. Now everything is ready. We'll create a job, water sloshing. We'll use four multiple CPUs. Precision, we are going to use a double precision, recommended double precision for this type of problem. Let's have a quick data check. So just put for a data check if there is any preprocessor thing related error. Yes, there is one thing is missing, which I realize. This we have to put one more boundary condition. We have to put this constraint in all direction, otherwise this will be created issue. That's what actually error it is given. So we are going to go to load. We are going to go to boundary condition, and this will be initial boundary condition, displacement, continue, and then we are going to put on this. You are going to constraint in all DOF except X. So now it is, everything is done. Let's do a data check now. So by the time data check is going on, let's check and quickly check the input file, how it looks. So it's done. So successfully done. We'll also go through the input file. We'll go through the input file, how the input file looks like. So you have contact, you are given gravity, you are given through some amplitude. Now this is important. So once you filled it, you can see initial condition, type, volume, and it takes this material assigned, whatever material we assigned, it's assigned to this inside element. Water property, amplitude. Let's see how far it can. So we'll submit it, and then just wait for result, how it looks like. Just before going into much result phase, we'll also look how the initial volume is filled. We'll look into that and then we'll wait for a result. Water properties. You can do a lot of things using CEL technique. I think not much tutorials available on YouTube or net. So we are going to do couple of more tutorials on this. So you have Eulerian mesh. The type will be EC3DR, and you have assembly. So I think run is started, so we can quickly check. I'm going to take a cut, Z cut, and I'm going to put in this plane, and I'm going to plot assembly, and this is what actually you see the filling. So immediately at 0 time step, you can see the 1 is fully filled with water, so it's immediately partially filled it with water. Within this domain you are filled with water. You can also look into, so you can see the rigid box, and then inside this is filled with water. So let's wait for the result, and then we'll discuss more on this. So guys, we finished the run, and right now what you see is a sloshing pattern, how the water is getting sloshed, and at the end you can see a droplet formation. We can also give longer time, and you can do at your end. You can run this for a longer time, something like a 0.30 millisecond, and see how you can see a different water falling down. A lot of things you can do. Now we are done this, so I'll just quickly show you how to do post processing, how you can see this type of thing. So that's pending thing from my side. So let me put this. So this is what it will looks. So for you it will looks like this. So there are two things you can do looking into sloshing pattern, how the water is getting sloshing. So you go to this view cut manager. So inside visualization you go to view cut manager, you put EVF void, you click that, and then you set this value to 0.5. so you see only the two part now, the box and the liquid, and then you can make it transparent. So making it transparent, you can see this, and then other things you can do is, like this was active, you see this is what active it looks like. So you make a box inactive, that way you can see the sloshing pattern. So this is number one thing. Number two things, how you can look into void fraction. So you go to the results, go to the field output, you go to the volume fraction for complete assembly, and then you apply that, and that way also I can take one cut along plane, and then you can also see how the volume fraction is changing from cell to cell. So this way also you are looking, but the good part is actually when you really look using this, you can get a feel how the water is getting sloshing, and then you can see a sloshing pattern. You can do a lot of things with this. So guys, this was a lot of people ask us, we want sloshing, water sloshing problem to be shown in SPH time, smooth particle hydrodynamics time, when we done that video. But then we thought it will be a good example to give to Abaqus community on the water sloshing, and a lot of people will get this learning for their projects and university projects or real-time examples. So thank you for watching this video. Don't forget to like us and subscribe us. Thank you. Bye bye.